Okay, well, I'll just say a few words and then give it over to Natasha. So Natasha has made she's from Kansas, as you see, Kansas State. She was recently a collaborator of one of our other speakers, Johan van der Leur and Victor Katz. And she's contributed a lot over a few years to the theory of integrable systems, very valuable contributions on different aspects, Yangian's R matrix theory, and in particular the construction either by bosonic or fermionic methods, what we call bosonic formulaic methods, of various sorts of tau functions. And I think that, I mean, the spirit of it is very much in the group representation theoretical setting, but that's really what the fermion boson constructions are all about. So anyway, it's a great pleasure to introduce Natasha Rozhkovskaya. I won't say the title because everyone sees it, and please go ahead.
Okay, so thank you very much for the invitation to speak at this seminar. And I'm very glad to continue this discussion on polynomial tau functions. And this discussion already includes several talks during the last few months. For us, it was a talk of John at our seminar at Kansas State University that he gave a few weeks ago. Also, the talk that is present in records of your seminar of John, and also the talk of Johan van der Leur a couple of weeks ago, also on polynomial tau functions and BKP identity, KP and BKP bilinear identities. And so my talk is related to all these, and this is just a continuation of conversation. And first, let me try to move the slide. So the world of soliton hierarchies, KP, BKP hierarchies, and other ones is very big, and people speak different dialects. So first, I would like to go over the general picture so that you would see what kind of language I'm going to speak today. So where is my part? So there is no Lux presentation in this picture because it is not going to be part of our conversation today. Here you probably cannot see it because it's in tiny letters. This is Kadamtsev-Petriashvili equation, and this is the equation in partial derivatives, nonlinear partial differential equation, and it has explicit solutions, which is quite surprising because that doesn't happen every day with the partial differential equations. And moreover, among these solutions, there are special kind of solutions which are called the solitons. These are waves with a special kind of behavior. And in the 20th century, there was a big question why soliton equations have these kind of solutions. And it turned out that the answer is in the hidden symmetries of this and other soliton equations, which can be described through the language of different parts of mathematics and physics. And here, this is the path that we will go today in explanation of these symmetries. So in particular, Kadamtsev-Petriashvili equation is not just on its own, but it is a part of a countable system of partial differential equations. And all this system corresponds to a system which is more algebraic. This is bilinear system of equations through the expression through Hirota derivatives. So all of them can be expressed through Hirota derivatives. And then there is more algebraic system, bilinear system of equations on some function which is called tau function. The solution of the system is called tau function. And then it turns out that all this system can be written in a compact form because every equation here is the result, the coefficient of Taylor decomposition of one bilinear identity written in Hirota derivatives. So this is formal series and in variables y. And when we decompose it into each particular term in powers of y, we get all these equations. And after that, people look at, there are several different interpretations of this bilinear identity. All of them are beautiful and amazing, a lot of beautiful things happen there. So that's why I personally fell in love with this part of mathematics and physics. And what happens is that people travel between different interpretations, and that helps them to get elegant proofs and different useful observations about solutions of this identity and different other facts. For example, one can look at boson-fermion correspondence. So here, the solutions of this identity, usually they are considered to be polynomials in some variables, which we will denote through the talk, variables PIs, or in the completion of this polynomial algebra. And for the boson-fermion correspondence, one can take the space which consists of these polynomial algebras as graded components, and then all this graded space can be identified with how to call it, exterior semi-infinite wedge product of some countable vector space. And then there is also bilinear identity, which corresponds to this one. And this is isomorphism not only of vector spaces, but models over different of Clifford algebra, Heisenberg algebra, gel infinity. Also, bilinear identity is nothing else but a description of an orbit of the vacuum vector in a wedge product of this vector space under the action of the group gel infinity. Or another interpretation comes from the following observation. So this polynomial algebra can be identified with the ring of symmetric functions, because it is known that the ring of symmetric functions is a polynomial algebra in power sums. And then one can look for the solutions of this bilinear identity in terms of looking at them as being symmetric functions. And in particular, it is known that a very famous object in symmetric functions, Schur symmetric function, is a solution of this identity. And then we can go back through these transitions back, and this way we can get a solution, an example of solution of this equation or the whole hierarchy. And today I'm going to live mostly in this part, on this island. So my talk is going to be today in the language of symmetric functions. So all this story is going to be in the language of symmetric functions. And I'm going to introduce notations and the main objects which will compose different, which we'll use in different statements today. So lambda will denote the ring of symmetric functions. So these are polynomials where you can ignore the number of variables, and they are invariant with respect to any permutations, finite permutations of variables. One important family which we will use it a lot today, is complete symmetric functions, which is given by this formula. And this is a small example of a complete symmetric function when we put two variables. Elementary symmetric functions have similar definition, but we do not allow repetitions here. So this is elementary symmetric function. Power sums are given by this formula. And for any partition lambda, we can introduce Schur symmetric functions as a ratio of two determinants. And here we assume that the number of variables here is at least as big as the length of the partition. So these are Schur symmetric functions. And then we have the following statements. First of all, Schur symmetric functions, when they are labeled by partitions, they form linear basis of the ring of symmetric functions. The second thing is that the ring of symmetric functions also is a polynomial ring, and there are several families that can be chosen as independent variables. Complete symmetric functions, elementary symmetric functions, and power sums, they all generate symmetric functions as a polynomial ring. And inconvenience, a little inconvenience when we when we talk about these things, is that there are a lot of different families of variables, and it's a little bit confusing. So to help us a little bit today, I put some color in these variables to distinguish them. So x's, black ones, that means that my polynomial is symmetric polynomial in these variables. So this is, for example, sure symmetric function, the definition. Then through the Jacobi through the identity, it can be expressed as a polynomial in complete symmetric functions. And this is how this polynomial looks like. So h's and e's, they have more or less equal role. And when we talk about boson-Fock space, we may need variables there, and usually they are identified with power sums. So that's why they're in green. So they refer to the picture in boson-Fock space. And if we express each of these polynomials, each of these complete symmetric functions as a polynomial in power sums and substitute into this formula, we express short symmetric function through power sums. So something like this. And in the ring of symmetric functions, there is a natural scalar product where short symmetric functions form orthonormal basis. And since there is a scalar product for any operator, we can define a joint operator by this formula. In particular, for multiplication by elements by symmetric functions. And it is known that if we take power sums, the joint operator is exactly differentiation by the same power sum, just a little bit normalized. Okay. Now, here a lot of things will be done in terms of formal distributions or quantum fields or generating functions. And I ask you to remember these generating functions because a lot of things will be constructed out of these four formal series. So the first one takes complete symmetric functions and combine them in just one generating function. So we can consider them as elements of lambda or as operators of multiplication by these symmetric functions. The same for elementary symmetric functions and for adjoint ones. And now also, if we express all these things in terms of power sums, we will get these exponential functions, and that should remind you pieces of vertex operators, which we often see in this story, right? So, so I just wanted to sort of match this with some other famous formulas so that you would know what my notations mean in terms of notations in other places. And this is a lemma, which is very simple and not difficult to prove. It's very straightforward, which gives us commutation relations between these operators in terms of their generating functions. So these are commutation relations between quantum fields. So this lemma is an exercise in the book of MacDonald on symmetric functions. So this is very not difficult result, so it's straightforward, but it is very powerful. And this is the base of proofs of many things that many other commutation relations that will appear later today. Okay, so few words about sure Q functions and BKP, KP stuff. Okay, so sure symmetric functions, as we already mentioned, they are examples of solutions of bilinear KP bilinear identity. So they're KP tau functions. And this was proved by Sato in 1981. And yeah, so when we consider them as polynomials in power sums. So in analogy to KP hierarchy, there is the BKP hierarchy, which I think since it's not the first talk in this series, we sort of understand about its existence. And the most famous example of tau function of BKP hierarchy, by BKP bilinear identity, is sure Q functions. This was proved by Yo in 1989, and this is the definition of sure Q function. So this is also a symmetric polynomial which has some kind of formula of this kind. And those who work with KP and BKP hierarchies and the identities and their solutions know that a lot of arguments in both cases go in parallel. So there are a lot of calculations which look very similar. So here we have charged free fermions, here we have neutral fermions, and a lot of calculations look very similar. And of course, it would be nice if it would be possible to do something together just once, so just in one calculation. And up to some point, this is possible if we recall the following fact, that both sure symmetric functions and sure Q functions are special cases, specializations of whole little polynomials. So up to some point, we can do some calculations with whole little polynomials, and then at the end, when we start to talk about the bilinear identities, we have to split and consider each case separately. But vertex operator presentation is here, and let us talk a little bit about this. So whole Littlewood polynomial combinatorial definition looks like this. And if you look back to the previous slide, you can see that sure Q function has exactly the same kind of structure. So when we substitute t equals 0, we get sure symmetric functions. T minus 1 gives us sure Q functions. And moreover, there is something that we can call in general sense generating function for whole Littlewood polynomials. Namely, let us consider the following expression. So what is this? So this is the generating function for complete symmetric functions. This is generating function for elementary symmetric functions. We just plugged in t, parameter t in the variable. And this is some correlator here. So we have this expression, which we can expand in powers of u, in monomials of u. And look at the coefficients. The coefficients will be symmetric functions which depend also on variable t, because here we have symmetric functions, right? And it turns out that if we look at those lambda here that are partitions, because they can be partitions and just some integer vectors, but those that are partitions exactly correspond to whole Littlewood polynomials. So when lambda is a partition, this is exactly a polynomial given by this formula. So in that sense, this expression is the generating function for whole Littlewood polynomials. Okay, and what is good here for us, for our purposes, is that whole Littlewood polynomials have a vertex operator presentation, the same as presentation by action of fermions to obtain sure symmetric functions, and the same for sure Q functions. So this presentation is due to Naihuan Jing, who discovered it in 1991. And in our joint work with my graduate student, we described this presentation in the form which I'm going to present here. So through these generating functions which we introduced earlier. So I would like to pay attention that we use only these building blocks from the symmetric functions. So we have here some deformation, but we don't introduce anything new. We use old building blocks to construct these vertex operators, and it turns out that they give us whole Littlewood polynomials. So two families, so two quantum fields. One consists of multiplication operators by elementary and complete symmetric functions with the parameter t in the generating function included. So this is a joint operator, so these are some kind of differentiations, and something symmetric here. Then from that lemma, which I mentioned, which is exercise in McDonald book, it's very easy to see that commutation relations of these two quantum fields are of the following kind. And you can see that this is some general version of fermion kind of relations. And moreover, from the same lemma, also, it's not difficult to show that if we take gamma plus this quantum field and apply it to vacuum vector many times with different variables, what we will get is the generating function for whole Littlewood polynomials. So exactly the one which we defined on the previous slide. So this is the result of application of several quantum fields to the vacuum vector. And then if we expand this part in monomials in U, then we get for free the result that each whole Littlewood polynomial can be represented as the result of application of these operators to the constant polynomial, to vacuum vector. Okay, so now to convince you that we did not go too far from our KP and BKP case, let me show you what happens when we go back to t equals 0 and t equals 1. So so how we reconstruct the KP case, charge 3 fermions. So we recall that ring of symmetric functions is a polynomial ring in power sums. We take countably many copies of the ring of symmetric functions. Each of them is a graded component of our boson-Fock space. Then we take those gamma plus and gamma minus, which we defined just recently, put t equals 0. And here we put some renormalization because there is some classical way to write down commutational relations between fermions. So that's why we want to get them so that it would be recognizable. So if we do all that stuff, this will be the final result. And these are two quantum fields. Their action on the graded component of the degree m. And if we expand these quantum fields and look at their coefficients, then it will be clear that the coefficients satisfy exactly charged 3 fermions relations. So they satisfy these relations. So that follows from that relation that we proved that we showed here. So it's just going down to this particular case. And also, I would like to pay your attention that sure symmetric functions, they fit very well and nicely in this picture, in the sense that they, how to say this, that fermions, charged 3 fermions, they're the ways, like they're lowering and raising operators, they allow us to travel between sure symmetric functions. So sure symmetric functions are part of this picture because of their vertex operator presentation using fermions. Okay, so they are part of this, of all this algebraic story. And how do we get back BKP case or neutral fermion case? So as planned, we take whole Littlewood polynomials, take parameter t equal -1, and now we make it act on the odd boson-Fock space. So we take part of symmetric functions, which is generated by odd power sums. So this is our odd boson-Fock space. And then if we look at this formal distribution expressed through symmetric functions for all blocks which we described earlier, if we expand it and look at the coefficients, then the commutation relation will be exactly the commutation relation of neutral fermions. So this is what we have. So this is how we reconstruct those two cases. Now, so why do we talk about this? So what do we have so far? We have examples of solutions of KP and BKP bilinear identities, S lambda and Q lambda. We know that there are particular cases of whole Littlewood polynomials. We know that whole Littlewood polynomials can be combined into some generating function. And we know that this generating function is the result of application of quantum fields to constant polynomial, to vacuum vector. So all this, so what do we want? We want more solutions of KP and BKP bilinear identities, and preferably all of them. So we want all polynomial solutions of KP and BKP bilinear identities. So this is what we want. And I would like to, so there are different ways to get all solutions. I would like to mention today 4 of them, which I know as of today. So probably there are more, but those 4 which I know that produce all solutions, not only examples, but all solutions. So one of them is shift in the Jacobi-Trudi formula, and this is what Johan told about in his talk. So I will talk just a little bit more on the next slide about this. Then renormalization of generating function for sure symmetric functions. Then lattices of KP and BKP taufunctions through vacuum expectation values. So this is a tribute to the work of John and Alexander Arlov. And another way to play with generating functions, but not renormalization, but re-expansion. So right now, maybe it's not clear what I mean by these general words, but we will see it just very soon. Okay, so what are these methods? So this is just one slide which is dedicated to the story which Johan told in his talk couple of weeks ago. So we can recall that sure symmetric functions, which we know are solutions of KP bilinear identity, which are tau functions, that they are expressed through Jacobi-Trudy identity through complete symmetric functions. And we can treat them as polynomials in power sums if we just express complete symmetric functions in power sums. Now, the result of Victor Katz and Johan van der Leur says that let us take this formula and let us introduce shifts of these variables by complex numbers. And they are all different here. So you see that they're all different. Then all these are going to be polynomial tau functions. And any polynomial tau functions up to multiplicative constants, so we may multiply by something here, is going to be of this form. So we can always find some constants so that our tau functions is going to look like this. So the full story was told by Johan in his talk. Now, this got some continuation, so this continuation. And so the next way to construct all polynomial tau functions is the following. So let us look at the generating function of sure symmetric functions. So remember, we had a generating function for whole Littlewood symmetric functions. Now let's put t equals 0 there. Then as coefficients, we will get sure symmetric functions. And here, this is what will be left from that expression, which was many, many slides before. So this is generating function for sure symmetric functions in terms of that when lambda is a partition, we get here sure symmetric function. Now, let us take a collection of formal Laurent series with coefficients and complex numbers. And now let us multiply by this Laurent series our function, our generating function. So this is what I'm going to do on this slide. So I took my generating function for sure symmetric functions and just multiplied it by a collection of Laurent series. So nothing really like big here, how it happens. And then let us expand it and look at the coefficients. And our result with Victor Katz and Johan van der Leur is that, first of all coefficients here are going to be, again, polynomial tau functions of KP bilinear identity. Any polynomial tau function appears here. We just have to choose appropriate Laurent series to construct this generating function. And moreover, the whole this generating function for these polynomial tau functions can be written as one big determinant. And then, of course, the coefficients also have some kind of Jacobi-Trudy identity. So this is also a determinant where these are coefficients of this renormalized generating function for complete symmetric functions. So polynomial tau functions have interpretation as coefficients of certain generating functions. Okay, so the next method which I would like to recall here is due to John and Alexander Arlov, and I learned about them from John's talk at our seminar and some of their joint papers, and I will refer to them. So I allowed myself to change some notations so that they would match the notations which I use in these slides. And I extract from the construction the following facts. First, we start with Heisenberg algebra, which we realize through the normal ordered product of fermions. Then we construct out of this Hamiltonian and then KP evolution operator. And also, an infinite invertible matrix is fixed. And then the following polynomial NP is constructed using this particular fixed invertible infinite matrix. And the standard way, we apply KP evolution operator. So the result is going to be some polynomial in P. And their statement, the result is that all polynomial tau functions, so these are polynomial tau functions, and all polynomial tau functions are of this form.
Just a comment,
Yes,
Natasha.
okay. I was waiting.
In general,
Yeah.
it only gives a polynomial if G is upper triangular. So this is bigger than just the polynomials.
Okay. So that's something that I would like to talk about later separately. Maybe not even like. I really would like to talk one day about this in more details. So unfortunately, we didn't have time after your talk at our seminar. So I'm still waiting for the opportunity. Okay, so but let's take it this way. Yeah, so that if G is upper triangular, then this is a polynomial tau function. If it's not upper triangular, then it is some tau function, right? So should I state it like this? John?
Yes, there's a Schur lattice labeled by the lambdas of of tau functions, but if the G is a general general infinite linear group element, then you can get something much more general than polynomials. But they have particular, I mean, certainly not the most general tau function, but they have particular properties which place them, like your polynomial ones, that it places them into particular Schubert cells.
Mm-hmm. Okay, so yes, okay. So let me just move on. So I want just to extract a few things out of here. So since my talk is related to polynomial tau functions, let's just stay there because it's safer for the moment, okay? And maybe some comments in the end of my talk, which I prepared, maybe they will be also related to this part of our conversation. So, but for the moment, let me just continue if you allow me. So what else I would like to extract from the constructions of your papers? I also would like to extract the fact that if we look at, if we take these p's and interpret them as power sums, then these polynomials will be symmetric polynomials, which look like Schur symmetric functions, but instead of monomials here, we write down, let's call it like in case of when we talk about polynomial solutions, where here we have a polynomial. So is this correct? Did I formulate it correctly here?
Yes, that's correct. That's
okay.
correct.
Okay. So now, and the last case, so I promised 4. So the last case, I'm going to do this with the example, first inspirational example, because this is something that is complete. So here, the part where I'm certain about everything, how it works. And then it will be more like generalization of this example, where there are still some places where I want to double check, but I want to present it here because I think that I present the statements which I think are correct. Okay, so which I'm certain are correct. Okay, so what is inspirational example? So here's going to be example. So what I'm going to show right now is not all polynomial tau functions of BKP case, but an example of such function. So let us take the definition of Schur Q function and let us change it, let us modify it. Exactly in the same way as Schur function was modified on the previous slide. So here in the definition of Schur Q function, there were monomials, x1 to the power lambda 1, x2 to the power lambda 2, and so on. And instead of these monomials, we put new polynomials, which are quite common in representation theory at least, which are some multi-parameter analogs of the power of x. So we fix a sequence of complex numbers, and instead of x to the power k, we consider this kind of polynomial. And we put this in the definition of Schur Q function, and we get something which is called multi-parameter Schur Q function. So this is symmetric polynomial, which is defined this way. So now I would like to tell you why I got interested in this particular example. So these multi-parameter Schur Q functions were introduced combinatorially by Volodya Ivanov in 2005. And for this reason, very often in the literature, they are called Ivanov functions. And also some combinatorial properties of these functions one can see in the work of Sergei Korotkih. Now, this is the reason why I was sort of paid attention to these symmetric functions, because they are eigenvalues of certain central elements. So in the universal enveloping algebras, so in the centers of the universal enveloping algebras of different Lie algebras, there are special kind of central elements which are called Capelli polynomials, so central elements. Since they are central on irreducible representations, they act as multiplication by a scalar. And there is a big question, how does this scalar look like? What is the eigenvalue of this central element? And in particular, if we take not even Lie algebra, but Lie superalgebra, queer Lie superalgebra, and take these central elements, their eigenvalues will be exactly described by factorial Schur-Q functions, which is particular case of multi-parameter Schur-Q functions. Also, they appear as generators for certain equivariant quantum cohomology rings, and they appeared when people started twisted versions of some one of Heisenberg category. So recently, in during the last how many 15, 20 years, they appeared several times, these Schur-Q functions, multi-parameter Schur-Q functions. And in our case, we are interested in them also because it turns out that they are polynomial solutions of BKP bilinear identities. So they are polynomial tau functions. And the main reason here, so why this combinatorial object also solves BKP bilinear identity. The main reason is in their relation to the classical Schur-Q functions, for those which we already know that they are solutions of BKP bilinear identity. Namely, they live in the same generating function, but we have to re-expand it in different terms. So this is generating function for Schur-Q functions. Again, we take whole Littlewood, put t equal -1, we get this expression, and the coefficients are Schur-Q functions when lambda is a strict partition, right? And something else when lambda is not a strict partition. Now, let us take exactly the same function, and we have to do a couple of technical things to make things work nicely. So first, just for the convenience, I have to go instead of u to 1 over u in variables. And also I have to take only positive part here. But anyway, it's more or less the same thing, plus some technical stuff. And then we re-expand this expression, but not in monomials u to the power lambda, but in this kind of factorial monomials. And look at the coefficients. The coefficients are going to be exactly multiparameter Schur-Q functions. And the fact that they live in the same generating function, which is realized by vertex operator representation, tells us that they are going to be solutions of KP identity, BKP identity, I'm sorry. So this is the reason. And this is the situation that we have. So this is inspiring example. So we have Schur-Q functions and multiparameter Schur-Q functions, and they are related by re-expansion of the same generating function. And for the rest of the talk, I would like to show you how this can be developed. This example can be developed into general construction of tau functions for BKP and KP hierarchy. And I claim that this way, again, all tau functions can be obtained. And this is very closely related to the construction of John and Alexander Arlov. So it's very close. So for the moment, I want to forget everything that I said before. I want to start with just in the middle of nowhere from the scratch. So let us take a quantum field of some operators acting on space W. So we're going to do something which is not related to KP, BKP, anything. So for the moment, we just forget about everything. Let's just take quantum field. So what does it mean? That it acts locally finitely, that for big enough i's, these operator, so if I fix a vector, for big enough i's, my coefficients are going to kill this vector. So this is the meaning that it is a quantum field. Now, let us take a matrix, infinite matrix. And for the moment, let us write down this expression. So just some combination of these operators and with these coefficients. Now, if it is living on its own, if it's just this formal expression, it's okay. So it's just, it is that it is. But as soon as we start to think about this guy living with other guys, like if we have algebraic structure, if we decide to look at some multiplication or commutators or some other things, then there is immediately the question, how we're going to collect the terms. Is this going to be a well-defined thing when we multiply or take commutators of these guys? And the answer will depend on the properties either of the initial quantum field or this matrix. So we have to introduce some more conditions if we want some algebraic structure of coming out of this construction. And this is, again, so we call this formal distribution. So let's assume for the moment that this is something that will be okay defined. So this is formal distribution, and we will use it as a notation on the next slides. Okay, so what conditions we can impose and what they get. So I'm going to talk about conditions on the matrix. And I sort of try to show them visually because otherwise it's a little bit difficult. So first of all, if I want this thing to be a well-defined expression, so that it would be a linear operating actor acting on the vector space, I can achieve this for general gamma if I take my matrix A, my infinite matrix, such that starting from in every row, starting from some point, I start to get 0, 0, 0, 0, 0. So if I have zeros on the right. In this case, since I started with the quantum field, every gamma tilde S is going to be a well-defined linear operator. Now, suppose that I want to get new one also to be a quantum field, not just a formal distribution, but a quantum field. This can be achieved if this staircase of last elements in each row is an increasing function, because then at some point I will just cross out this place where I start to get zeros when I apply to a particular f. Okay, so moreover, suppose that I started with some operators which satisfy relations of free fermions like KP case. Let me take two matrices, matrix A and matrix B, and let me construct these new elements here. So suppose that these are well defined. By the way, I want to say that for the rest of the talk, my condition number one, it will be assumed that it so I will assume that so the matrix satisfies my first condition, that everything is well defined. So here I took these two modifications, change of basis, and then my new psi plus minus tildes will be also charged free fermions if and only if I have some symmetry between matrices A and B, and this is exactly the symmetry. And the same for neutral fermions. I can modify my fermions, and this is what I get here. Okay, so let me go to the next slide. And now we have all these observations. So let me go back to general gamma, not necessarily fermions or neutral fermions. Let's start to apply them to different, to a vector in our vector space, and let us see what are the results.
I have a question. Can I?
Yes. Yes.
So are those conditions equivalent to saying that the bilinears, which are the currents, are still the same?
Like
if I take psi plus minus normal ordered, then will it be still the same current after I rotate the fields, because A minus 1 is B check?
So what does mean the same current? I don't understand quite well.
So let's consider the charge current, which is normal ordered of the two.
Yes. Okay. So you mean what happens if I take normal ordered products? Whether it's going to be the same, like sorry, I have to translate my language.
Heisenberg.
I don't know. I did not check this, but it's quite possible. Yes.
It looks like exactly that condition. If I rotate the modes of psi plus, they must rotate.
Yes, it's quite because the normal ordered product, these will cancel each other, right? Yeah. So yes, it's quite. I just didn't think about this. Yes. So okay. I did not consider Heisenberg here in this part. So, but it's quite possible, yes. Yeah, yeah. So I wouldn't.
Could I just ask to explain the plus minus in the charged free fermions? What does the plus minus mean?
Here, plus minus.
Yeah, what is the role of the plus minus in the charged free fermions? Usually, there's no such thing.
Okay, so there are operate. Okay, so if we go to fermionic Fock space, so pluses are the ones where you add one more vector.
Oh, I see. The plus. Oh, the plus
you
is the creation, the minus is the annihilation. I'm sorry. Okay.
Yeah.
Okay, it's just different notation. Fine. So I would call that psi inside that. Okay.
Yeah. So that's one more difficulty that we speak.
No, everyone has their own notation. But I think Fabrizio's question is probably the answer is probably yes, because the currents, of course, you know what you call the Hamiltonians, so the generating function of the Hamiltonians. The currents are just bilinears in the psi and the psi dagger, right? The current generator is just bilinear in that, and you've got them in a sort of dual relationship, A inverse equals B check, and that probably is just what's required for the currents to be invariant. That's what Fabrizio was asking.
I think I understood what he asked, and he looked satisfied. I don't know.
Oh, okay, fine. So I was just catching up.
What the answer from Natasha was.
Yeah. Okay. So then let me just keep going. Okay, so now we take this modified quantum field and just do some trivial statements. So this was my initial quantum field, initial gammas, where I started. I apply them to some element of my vector space, so some operators. Okay, so, and let me call this f lambda. And these are like change of basis, modified ones. Then, of course, it is trivial because of the relation between these two that we can go back and forth. What are the relations between f lambdas and f tilde lambdas? So here we have also to assume that our matrix is invertible. So to write down this. So that's also clear. Okay. Now, remember, we like to talk about generating functions because they produce different nice solutions of different identities for us. So this is our initial situation, so initial thing. So I took quantum fields and I applied them to some vector f. This is going to be some formal distribution, and the coefficients are f lambdas, which we just looked the slide before. And then we can do the following. We can take this new generating function, and we don't want to introduce anything new after we modify it. We just want to take exactly the same generating function, but re-expand it. And it is possible if the matrix A is invertible. And here we are going to have, instead of monomials, in general, some formal complex value distributions. But these are going to be those f tilde lambda, which we just expressed. So this is exactly what happens in the case in my inspirational example, that I started with Shurq functions, and this is what I had. And this is multi-parameter Shurq functions, and this is what I have, like some multi-parameter, there was some multi-parameter rational functions there. Okay, and now let us go further down. Let us apply this to whole Littlewood polynomials. So I remind you that whole Littlewood polynomials were realized by application of gamma pluses. Several gamma pluses applied to one gave us whole Littlewood polynomial. Now let us apply our construction, and let us change this by this expression. And just to be on the safe side, I assume that A is a nice matrix. It has that finite property that everything is finite and well-defined. So in other cases, I don't know, maybe it's possible, but I didn't look carefully. I want to be very careful there. And it turns out that if we do this manipulation with vertex operators, which realize whole Littlewood polynomial, it is going to be the same thing as to take the definition of whole Littlewood polynomial. This is the definition. And here, instead of monomials, x to the power lambda, write down these products, f lambda, so on. So, and these f lambdas, how they come? They come as polynomials which come from that matrix which we took in the very beginning. So we take definition of whole little polynomials and substitute monomials by some other polynomials. And next thing is what? So it's just a formulation, reformulation in this particular case. So we take generating function for whole little polynomials, and then for those new ones for which we have a formula, combinatorial formula written on the previous slide, they appear as coefficients in this new expansion. So it is just re-expansion of the old stuff. And why do we talk about this? Let us go to the case of KP, to the KP case, or to the case when t equals 0. And if we go through all this stuff, here we will get the ratio of determinants, which is no surprise. But here I would like to pay your attention that I'm going to get this polynomial multiplied by x to this monomial. And just in a few slides, I'm going to make a comment on this. Okay, so I'm going to make a comment on this. So why do we have this monomial? Why don't we have just something here? And let me tell you what properties we get for free from this construction. So first of all, we get stability property, which is quite important in this part of our story, because it allows us to construct transitions between, it gives us algebraic structures acting on this space. So as lambdas are part of this story of action of different vertex operators, they don't depend on the number of variables in the definition. So these polynomials which we constructed, they have stability property. That's just easy consequence of our construction. The next thing is that immediately we know that these polynomials, even for we change the formula, the definition, right? They are the result of application of these operators, which are not very different from fermions, as we just discussed, right? So these are result of, there is a vertex operator presentation of these polynomials. And because of this property, it immediately follows that they are tau functions of KP bilinear identity. And since exactly these kind of things appeared when we proved our result with Victor and John, and by the way, that result was also proved by similar methods which I described today. Any polynomial tau function is of this form. So it's going, any polynomial tau function we can write down as the result of re-expansion of generating function for sure symmetric functions. And also there is a Jacobi-Trudi identity here. And the final thing which I would like to discuss is this subtle question. So why do we have this x to the power n minus g here, rather than it would be probably nicer to have here something like this? So why do we not get here this kind of thing? And it's a very subtle question which is not obvious. So let me explain you my point of view on what's going on here. So first of all, of course, and this was proved by John and Alexander Arlov, this is of course a KP tau function. So this is also a solution of KP identity. So for any fixed lambda, it is a tau function. However, in general, it may happen that our choice of these polynomials, so let's assume that these are polynomials. If these are polynomials, we can substitute 0 instead of variables, right? It's not a stable family of symmetric polynomials, meaning that if I plug in 0, my formula will change. Okay, so it's not going to be the same formula depending on the number of variables. And this is some kind of obstruction or inconvenience when we start to talk about algebraic structures, like action of things that look like fermions and the Heisenberg algebra or gel infinity, about raising and lowering operators. So I try to explain my understanding of this situation in this picture. So this is my final thing that I want to share this. So this is final piece of information. So this is the example of sure symmetric function. This is the definition, combinatorial definition of sure symmetric function. They are stable. And the reason the thing that they are stable is implicitly used in the fact that here we have all these fermions going back and forth, like raising and lowering operators. And they have this nice algebraic structure. When we define them, we don't remember how many variables were there in this definition. They never appear in this definition. So we have well-defined action of Clifford algebra or charge-free fermions here. And these S lambdas are part of this picture. So these lattice, we can travel along this lattice using these fermions. Now, let me take this formula, which appears quite often in many applications in many parts of mathematics. For example, factorial sure functions, there are many versions of them, and I'm a little bit lost which definition is which. But this is quite common situation, generalization of short symmetric functions, and they have a lot of applications. However, it may happen that this formula is not stable, that if I plug in xn equals 0, I will not get the same formula here for another number of variables. And that makes it difficult to define algebraic structure on transitions between them. So we can consider the set of transitions between them, just lowering and raising operators. But to describe commutation relations between them, or what kind of algebraic structure is that, it's going to be at least messy, so not canonical for sure. So there may be some difficulties. And if we go to this example, which appeared naturally in our construction, it just showed up itself, so we did not invent it. Then this is again stable. That was just the result. And there is again the algebraic structure which allows to travel along all these parts. And in general, I can take this lattice and match it with that lattice, for example, in one point. I can match these two definitions. I can find out the polynomial here so that I can match this polynomial in one point, maybe a few points. But most of the points of this lattice will be off. So as a totality, this one has more difficulties with algebraic structures than this one when we have this monomial here in this part. So that's probably all that I wanted to share today. I would like to thank you very much and show you this small greeting from Kansas from our local photographer. Okay, so thank you very much.
Thank you very much. Okay, good. So I'll open it up for questions then, please.
Well, I don't want to butt in immediately if there are other people who have comments, because I do have quite a few comments, but I'm not sure they will be of interest to everybody. Does somebody else want to make a comment first?
Let's see.
Well, if not, then I'll go ahead. So that formula, the generalization of the Jacobi bi-alternant formula, where you replace the monomials by essentially arbitrary consecutive degree polynomials, not necessarily monomials. It was not first derived, of course, in our paper with Sasha Orlov. That was just a sort of spin-off of what we did. And in fact, special cases go back to Biedenharn and various other people for special non-homogeneous polynomial, non-monomial entries. But there was something which was inspired by some work of Veselov and Sergeyev of about 15 years ago. And there was a paper written together with Lee and myself, in which this formula was derived as a sort of illustration of the universality of the interpretation of these tau functions as Plücker coordinates. I mean, you can think of Schur functions as Plücker coordinates of some special canonical element in the Grassmannian, but similarly, other tau functions can be viewed also as Plücker coordinates, and one has these so-called Jambelli identities which relate them. But the Jacobi-Trudi identity, which you were emphasizing, the way that we constructed it, I mean, from these bi-alternant formulae, ratios of alternants, they had a sort of generalized Jacobi-Trudi formula, like you have. What you have is you multiply this by these monomials. But we did not do that. What we did, and this I think is related to your remark about sort of saturation phenomena. We had an extra index, and the way that we understood that, so the things that generalize the complete symmetric functions did not carry just one index. They carried a second index, an upper index. And we interpreted this, because this was not the only instance of such things. We interpreted this as a quantum, as a parameter in a quantum expansion in powers of Planck's constant. And the Jacobi-Trudi identity, this extra integer plays a role. So it's not exactly the same as the usual Jacobi-Trudi identity. There's a shift, and the shift is exactly related to the number of x variables. So the way that we understood this was that the Schur functions, if you change the number of x variables, indeed they don't have this kind of stabilization property that you say, but they are nevertheless Schur functions restricted to that number of polynomial variables. And what we understood was that fermionically, these represented vacuum expectation values in different charge sectors. So it was not in the same charge sector. The charge was related to the number of x variables in which we had symmetric polynomials. And that there was already an example of this in the work of Veselov and Sergeyev, and they already referred to even earlier work by Reshetichin and someone else, which actually was in a different context, but in which they referred to these as quantum Jacobi-Trudi identities. And that's exactly what we have. We have a quantum Jacobi-Trudi identity. And I think that that is somehow equivalent to what in your formulae involves multiplication by these monomials. I mean, multiplication of the factors in the determinant by these monomial terms. So we can speak more about it in detail, but this phenomenon of quantum Jacobi-Trudi identities is not a new thing. It's something that goes back about 20 years. And that's another way to interpret the way that the Jacobi-Trudi formula gets modified when you replace the monomials by general polynomials.
I think it's just the matter of not even mental, like all my life I was working with symmetric functions where stability was important, and it's just sitting very deep in my mind that stability is better than not stability. And that's why when I see that there is no stability, I think, oh, there is no stability, maybe I should be a little bit cautious about this. So that's the only reason. But I know that there are a lot of applications where stability is not necessary. So that's
you're absolutely right. That was something that really troubled us when we were working on this, that somehow the number of x variables was a sort of hidden variable which changed really what the tau function was. And you don't exactly what you're saying, that you didn't have just by restriction. You didn't recover the lower end values just by restriction, and that was troubling, but that's what happened.
Yeah, it is what it is. I mean, nature is nature.
But more recently, in the work with Arlov, we had some insight into what that meant, and it really was that you have, in the case of Schur functions, you can give a vacuum expectation value representation like what you gave, in which you've got the exponential of the current operator, and you have a group element, but the group element is the identity, and then that acts on some basis element lambda. But you can take the expectation value in not just in the vacuum, but in any charge sector, and you get the same Schur function. That's a sort of degeneracy which is very peculiar to that case. Whereas in general, if you do more general types of polynomial tau functions, it does make a difference which fermionic charge sector you're in, and that's what that's how this sort of non-stability gets reflected. They're not the same functions.
Okay.
Okay. Afterwards, perhaps when we speak privately, I have more to say about that, but I don't want to bore the rest of the audience. And those who are really interested will stay on.
Let's see if we have more questions from the audience. I do have a very basic question. So there are all these different ways to describe all polynomial tau functions, as I understand. And so what is the connection between these? So there's the shift version by Johan van der Leer and Victor Katz, and there's your version. So how do you translate one into the other? What is the dictionary between them? Is that easy or clear?
So the translation between Johan's and like this with Victor and Johan, it's basically technical. You can put all these shifts into Laurent polynomials. You can put them inside.
Okay.
So
okay.
and it's explained as a remark in our paper. Now the connection between John's and the other ones, I would leave to John to explain, so that he would do it better.
Yeah. I'll explain it afterwards.
Yeah.
There's a one-to-one course. It really is a one-to-one correspondence. Well,
Yeah.
one-to-one with a caveat. Remember that Victor, well, rather Johan, when he was speaking, he emphasized that there were various choices of the translation constants that gave the same Tau function, that you had to somehow or other take a canonical choice. And we also have exactly that. And it has to do with, roughly speaking, it has to do with shoving in an arbitrary stabilizer of the vacuum.
Okay. Mm-hmm.
Okay. And the last part, and so I would say like both generating functions multiplying by something in front and generating functions re-expanding in new bases. These are sort of a little bit, so you take a collection of tau functions and break them into parts, and each part is a generating function, or you break them into different parts and put in different generating functions. So there are like overlaps when it is the same thing, but usually these generating functions are like different things. Okay, so I just don't know how to say this.
I don't know if William has left yet, but there was a comment I wanted to address to him. William, are you still there?
I don't see anyone.
Too bad. Well, because it's a quantum field theoretic question. Okay, I'm going to just throw this out. It's too bad because he might have known the answer to this. William is the other organizer of the seminar. And he does a lot of work in quantum field theory and condensed matter and so on. The transformation that you made, I don't know if I quite followed it, but the transformation that you made when you took what you called quantum fields and then replaced them by some linear combinations of these quantum fields. And if I understood correctly, you were showing a way to change from sure functions to these more general things. It looks to me, this is just a word, but it's something which is important in quantum field theory. I think that what you're doing is what is called a Bogolyubov transformation. And that's a well-known thing in quantum field theory. Actually, maybe Fabrizio, you know what a Bogolyubov transformation is? It's a non-unitary transformation, which acts on the operators. It doesn't really act on the states, but it's a linear operation, so it looks very much like what you're doing. And it's I think in terms of integrable systems specialists, it's a sort of dressing transformation. But it has a very long history in quantum field theory, and I don't remember what the importance of it, but it's dealt with in particular in Bogolyubov's book. So it might be worthwhile to look up what is a Bogoliubov transformation, and you may actually have been stumbling across exactly that.
I thought the Bogoliubov transformation is something more complicated, honestly. Yeah. This is just like change of basis, linear basis.
Well, you know, in integrable systems, when we talk about inverse problems, actually, maybe we should end the seminar
maybe
and
this
say,
would be, yeah, I would say that this is a good point to finish the official seminar, and whoever is interested, we'll
yeah, we can continue talking, but thank you very much for